So now what we want to do here is that we want to talk about light transmission by polarizing sheets. So we want to talk about light transmission through polarized sheets. So when I think about a polarized sheet, I'm literally imagining a plastic sheet like this that looks sort of like, you look at this thing and it looks like, maybe sunglasses or something like that. So, but I want to look at the details of this sheet here. So one of the things that I imagine here is that when I look at the light coming into a polarizer, what actually happens here. So if you look at the image on the screen here, let me turn off the light so that we can get a better image. What you're seeing here is that I have unpolarized light, and it has many directions, but we can always break these vectors down into a y and a z component. So as they come through, we just showed that if it goes through a grid system, anything that's parallel to the grid gets absorbed. Anything that's perpendicular to the grid is what actually gets through. And so I have this wave here that is now vertically polarized, and it's going through this thing. So what I want to do right now is that I want to look at this intensity, and then I want to look at the intensity afterwards to actually start getting a handle on what actually happens here. So I'm going to turn the lights on and then go back to the board. So from that image that I just showed you here, you could imagine that I have incident unpolarized light. So that means I'm getting light that's coming in that looks like this. So I have unpolarized light. And what I'm going to find here is that if I put a polarizer through this thing, and let's say what we just had right now is the image showed that I had a horizontal polarizer. What the horizontal polarizer does is it takes the component parallel to the polarizing grid here. So if I'm looking at a wave that's moving in this direction, afterwards the component that gets through is the one perpendicular to the grid. So that means here is that I'm only seeing half the light coming through this polarizer. Now, a good thing that we should do here is to number the polarizer, since we're going to be dealing with multiple polarization sheets here. So if I have this guy as the initial intensity, this is before the polarizer, the intensity of light afterwards, I'm going to call I1, and that means here, I'm going to call this polarizer number 1. So if I look at this thing here, you can see that it took out half the light. So therefore, what we should be writing here is that the intensity after the polarizer should then be half of the initial one. And this guy here is what we call the 1/2 rule, because it took out half the light. But one thing that you fail to probably realize is that this 1/2 rule is independent of the direction of this polarizer. So for example, we could look at other examples here. So let me state this before I move on. So the critical thing here is that the the only component of polarization that goes through is the perpendicular component. So the key word here is what? Perpendicular component. So if I look at some examples here, let's look at them. So one example that we can do here is that you can imagine that I have a vertical polarizer. And if I had a vertical polarizer, what's it going to take out? I'm going to get the vertical one that's taken out, so then afterwards it's going to be the horizontal one. But what happens if I have one that's not horizontal and not vertical, but is angled? So for example here is that, so if I look at this example here, imagine that I have a polarizer that looks like this here. If it looks like this, if I have light that's unpolarized, that's coming in, the only component that survives is the perpendicular component. So that means the only component that's going to get through here is the one that's perpendicular to the polarization axis here. So that means that when the light comes through, it's at this angle here. That's the component that actually survives from this thing. So when I look at the intensity of this guy here, I have that amount of incident light. Afterwards, I'm still going to only get half the light. Because, why? It's taking out half the components here. And I can actually switch it the other direction. And if I switch it the other direction, and I look at it like this, and I send in unpolarized light again, you could imagine that if this is the incident polarization here, then the direction of the component that's going to survive the polarizer then angles in the opposite direction of what we just did right here. So this intensity would also be I naught equal to 1/2 I initial here. So once again, the 1/2 rule not only doesn't apply to the horizontal and vertical ones, it also applies to these directional ones. So now what I want to do here is that I'm going to imagine that I have a polarizer like this, and now we have to include the angle of this polarizer here. So what I want to do here is that I want to suppose that the incident light is already polarized. Now the easiest scenario is this guy right here. So you could imagine that I have a polarizer like I just had right now that looks like it has a polarization like this. So then the wave that comes out of this thing is then going to be perpendicular like this here. And to make it easy here, you could imagine that now I have a second polarizer, and this time I'm going to make it horizontal so that it looks like this here. Now, one of the things that you want to pay a difference between these two here is that the angle of polarization between this guy and that guy are the ones that we want to pay attention to. So when I look at these things here, there's an angle difference, delta theta, and this guy here is the angle difference between polarizer number 1 and number 2. So if I label these guys in the language that we've been talking about, this is number 1 and this is polarizer number 2 here. So picture-wise, we know that if this is the incident light coming to the polarizer, we know that only the perpendicular component survives. So when I look at this guy here, the only thing that's going to come through this thing here is going to be what? This perpendicular component. So when this light comes in, we can see that part of the polarization is taken out by this filter here. So what we should expect here is that the intensity compared to after polarizer 1 compared to polarizer 2 should be different. I should have less light because I'm taking part of the light out here. So when I compare intensity 1 here to intensity 2, what we expect here is this. We expect that intensity 1 should be greater than intensity 2, since why? We filtered out some polarization components. Okay, so the question is, how do you determine how much intensity actually got decreased? So what I want to do here is I want to redraw this polarizer. And what I want to do here is that at this point, we're taking this polarizer and we're holding it like this, but the image that I want to look at is I want to take this polarizer and I want to look at it like this here. Okay, so if I draw this, this is what this polarizer should look like. So I imagine that the polarizer, I could draw, actually I'm going to draw a square because that's closer to what we're seeing here. So let's draw this square polarizer. So I have this square polarizer that looks like this. So when I look at the polarization, look at that this guy's horizontal. So if I look at this thing horizontal, it's going to look like this here. So when the light comes in, it's coming in at an angle. What angle is this? Well, this angle is going to look like this. So this is how the incident light sees the polarizer. Now, the notation that we use for measuring angles is everything is measured relative to the vertical here. So I'm going to pick this, oops, it's good enough. I'm going to pick theta here equal to 0, and then theta here is going to be 90 degrees here. And it's actually common to pick positive in the negative direction. But since it's arbitrary, it doesn't really matter for right now. And so what you see here is that this polarization is off angle, and this angle between here and here is what we're going to call d theta right there. Okay? That's angle turns out to be the difference in angle between this polarizer and that polarizer right there. Okay? So now, let's look at this. The only surviving component is the perpendicular component. Any component that's parallel to the grid is going to get what? Absorbed. So now, let's break up this guy here. And so what you're seeing here is that you're seeing this. I can take this field component and I can break it down into a component that's parallel. This component right here is going to get what? That gets absorbed by the polarizer. And then I have a vertical component that looks like this. This guy right here is the transmitted component. So we know that that's the one that's going to get transmitted. And so now, if the angle here is the vertical, look at the sides now. If you look at the vertical component, it's what? It's the adjacent to the angle. If you look at the one that's parallel to the polarizer, that is opposite to the angle. So therefore, this guy's associated with the sine, this guy's associated with the cosine. So when I look at this thing here, if the intensity that is coming in is this guy called I1, what you're going to find here, I'm going to now look at the amplitude. So if I redraw that triangle, this is what I get. I get this guy right here, and this is the component, this is the amplitude, and that amplitude is a vector. And so when I now break this guy up, I have a vertical component like this, and then I have a horizontal component like this. If this angle right here is d theta, then this guy should be E naught cosine of d theta. This should be E naught sine of d theta. And what you're seeing here is that that guy goes to 0 and it gets absorbed. The only surviving component is this cosine. So then that means the surviving component is equal then to E naught cosine theta here. But remember what the intensity is? The intensity is equal to I, and that has to be amplitude squared. So this has to be E naught cosine squared theta. By the way, I should not have called that E naught. Why? Because I called that I. So I should come back and I should stick with my I here instead of the naught here. So let me go back and change that. I know it's easier for me than you. So if I put this in, I have 1, 1, and then of course this is 1 right here. And if I come over here, this is 1, 1, and this guy's going to be 2 here. So when you look at this here, then if I rewrite this, this is going to be what? E1 squared cosine squared theta, but E1 squared is the same as I1 cosine squared theta. And this is I2. So the intensity is proportional to the cosine squared. So now, if I look at the intensity of the light coming through the polarizer, then I could say here, if I was to summarize the whole thing, then it looks something like this. Let me erase this. So then our example is, I start with unpolarized light. It's coming in, and it has initial intensity of 0. I naught, excuse me. Then we had a polarizer that did what? It was at an angle like this. So therefore, the perpendicular component is what goes through. And as it goes through, that means it's angled off like this here. And this now has intensity I naught. It took out half of the components, so I get 1/2 I naught. And then I had a second polarizer that looks like this. And this is polarizer number 2. Only the perpendicular component gets through. And then this guy is this one here. And what we expected here, that the intensity at 2 to be smaller here. And we saw that the intensity then follows this cosine squared delta theta. Well, what is delta theta? delta theta is the angle between the two adjacent polarizers. So if I look at the final intensity of the light then here, we can then see that the intensity 2 is I1 cosine squared delta theta, which is equal to what? I naught here is the 1/2, so then I'm going to get I naught, and then I'm going to get half the light, and then the second polarizer gives me this, and you're seeing that this intensity then got diminished as it goes along. So that's how you deal with these polarizers here. So now what we got to do here is that to complete the discussion on polarization, we want to go through the example. Okay, so let's go through the example here.